So before we talked about real valued functions, but let's go ahead and start kicking ourselves into what calculus really is. So if I were to take, let's make a new note. Note 1. Let's talk about classifications. Classifications of real valued functions. My handwriting might be a bit messy, but if we were to have a algebraic functions, this could be, for example, like polynomial functions. Polynomial. I'm just going to say polynomials. And this could be a constant in which x, y equals 3. This could be a linear function, linear, in which x, y equals 3x. This could be a quadratic function, quadratic, I think I spelled that right, function, in which y equals 3x squared. And this can also go on into like a binomial in which y equals 3x squared plus 2x, or a trinomial minus 1. And of course, this could also be a cubic function. Cubic function. Ex. I always forget the x's. Ex. Y equals 3x cubed. And it's just etc, etc, etc. Anything can happen, etc. etc. There we go. It's just a matter of what we are dealing with. All of these are technically considered polynomials. All these are technically considered polynomials, and they're all algebraic functions. So let's go ahead and establish what a rational number is. A rational number, rational, let's go ahead and rewrite that. Rational number is any integer and integer over integer not equal to 0. So this is anything that's a rational number. So when you define it like this, I've always had trouble with what rational numbers were when I was younger, because we had to remember like the entire number chart, I believe. This includes anything that's fractions. Because it's anything. This could be 1 over 10 million, and it's still rational numbers. This could be a whole number. This could also be negative numbers. I mean, I could have also just been like, I could have just had a hard time with this anyway, but once it's defined like this, it makes it so much easier to understand what a rational number is. And the same way applies to a rational function. So a rational function, let's go ahead and actually give ourselves a bit of space. So a rational function, it's similar to what a rational number is. So a rational function is equal to any function, any polyfunction. Let's just say that polyfunction. So I'm just going to say that's short for polynomial function over a polyfunction that is not equal to 0. As you can see, we just switched from integer to polyfunction. Polyfunction, integer. And with this difference, it doesn't do much. We just established that this could be any rational function, and we established that rational functions can be a constant. Let me move this up. It could be a constant, a linear function, a quadratic function, a cubic function, etc., whether it be quartet or whatever is passed to the fourth power. Um, is it cinquet or something? I don't know, but uh, these are just polynomial functions. This is a rational function, and that's one thing to look at classification of real value functions. But that was only part A. Let's go ahead, take a look at a new thing. I'm going to go ahead and clear my screen a bit. Alright, let's take a look into what else is a real valued function. And let's take a look at part B. We're going to be calling these transcendental functions. And this is really just a really fancy name for anything that's non-algebraic function. Non-algebraic function. And this could be your trigonometric function, so trigonometry, trig. This could be your exponential functions, and this could also be your logarithmic functions. So, for example, sine x, e to the x, and log, so ln x. These are transcendental functions. And then last but not least, we have our piecewise functions. Piecewise. This is the third case for a rational or real valued functions. So a piecewise function is, to define it quickly, is just different functions at, I should really put my handwriting neater. Getting more used to how I normally write. Doesn't mean that's not messy to begin with. Functions at different domains. Or not different domains. That's a bad way to put it. Domain's only one. Different parts of the domain. There we go. That stretched the screen a bit. So this could be, for example, equals x, the absolute value of x. And for those guys who don't know this, the absolute value of x actually equals x at all values, all values that are equal or greater than or equal to 0, and negative x at all values less than 0. And that should create a graph that looks similar to this. I guess a bit more neater. There we go. And this is what a real valued function is. Now that we got that one down, go ahead, give ourselves a bit more space, and let's start taking a look at the numerical representations of real valued functions using a table. So if we were to do, let's just go, let's name this note 2. Note note 2. And let's just call this a numerical representation. Numerical representation. I'm not gonna write the word representation after this. Using a table, we could just say that EXA is just a simple table. So for each x value, there's a y value. So for 0, let's just take 1/2. For 1, we could say 10. For -1, there's 1/2 again. And for 3, there's -5. There we go. And this could be just a regular function. Now let's write the symbolic representation. I'm just going to say symbolic. We could just say e to the x. Or sorry, not e to the x. Example of this would be y equals 3x minus 7. And we could also write this as f of x. If we remember, f of x is similar to y, but that equals 3x minus 7. And both cases work. When you get into showing your work, you have to make sure you stick to one y or f of x. And last but not least, the graphical representation. Graphical. For example, if we have y equals f of x equals set of all solutions x, y satisfying y equals f of x. So let's take the value that we had here. So if we had ex, for example, ex, y equals 3x minus 7. We could plug this into the calculator and let's just choose 3 random solutions. If we were to plug in 0, for example, x equals 0, we could get y equals 7, -7 actually, -7. And this would create a value of 0, -7. If we were to plug in another solution, and notice how I'm specifying that it's one solution, because there's no way you could have multiple solutions to an x value without it not being a function. So let's just do 1. This would create a value, so 3 minus -7, or 3 minus 7 is -4. And this would create a new point called 1, -4. And of course, we could create a new function, or sorry, a new value called like 7/3. And this would be 7 minus 7, so y equals 0. And we could say 7/3 is equal to 0. And that will be 1 point. So if we were to draw a graph of this and plot these points down, so if we have 1, 7/3, and of course we have 0 here, so I'm going to create dots for these. We could say 7 down here, 4 here, and 0. So I'm just going to create these waypoints. Oh, I made a mistake actually. No, I didn't. And 4 right here, and then 7 right here. I may have made a bad graph, but it should be linear in case that wasn't probably right. Should be very linear. Maybe I should just move this a bit closer so it shouldn't be that bad. And this would be our 7 over thirds. And that is our 7 thirds. There you go. But as you can see, we plotted all 3 points down. Each of them has one solution. To clarify the one solution methodology, so if we had, say, a circle, so we had x minus h squared plus y minus h, or y minus k. And this would be the function 2 equals r squared. This would be the function to a circle, right? So we're to draw a circle. You may remember this from algebra class, or even in your pre-calc class itself. Since x, let's just say this is -4, since x has 2 values at -4, it immediately makes this fail the vertical line test. So if we draw a vertical line anywhere, and it has more than 2 points touching the line, then it will create a big X and say that is not a function. And that is why we want 1 point per X value, or 1 point per set A, or 1 point per each value in the domain.